Suppose if we take this is coming under nuclear fusion. In this nuclear fusion, what he says here, status 3, solid 40 problems. Okay, then no problem. Right, in this nuclear fusion, here, the lighter nuclei means what they found, like the deuterium or proton. Okay, the deuterium, suppose H12 combines with another H12. Okay, two deuterium combined together, fused together. Then it forms one helium stable nucleus. Okay, He24 nano. It is stable plus some amount of energy. Q. Q is nothing but energy released due to the mass effect. And here also the mass effect of parent is more than, sorry, the mass of parent nuclei is more than the mass of daughter nucleus. So mass effect will be there, and that is released in the form of energy. So it is not endothermic, it is also exothermic reaction. And in this exothermic reaction, nearly some 23 to 27 MeV of energy is released now. Okay, Q is equals to what I am saying, nearly. It is appeared to be less compared to the fission in one reaction. But that doesn't mean here in the nuclear fission, less amount of energy is released. That we have to understand it later. Okay. Another type is here, suppose 4 protons directly. H11 plus H11 plus H11 plus H11. 4 protons combined. It also releases one stable nucleus, helium He24. And additionally, to balance the reaction, 2 positrons will be released. And some amount of energy is released again because of mass effect. It is also exothermic reaction. All are exothermic reactions. Okay. These are the two possible reactions they found here in the nuclear fusion. Okay. Sir, deuterium and protons only you took, sir. Is it not possible at least to combine He24 plus He24 or Li36 plus Li36 like? If you argue, then what he says, just to combine here, the very lighter nuclei, proton and deuteron, here, directly they won't combine because of the electrostatic repulsion between the nuclei. Means one nucleus, suppose bombarded with another nucleus, then problem here is, suppose this is proton. Okay, if you bombard with another proton, because of repulsive force, that too when it comes close to each other, when the distance is less, repulsive force is more. That's why because of that repulsive force, they won't actually come close to each other and not even touch each other. Okay. This one in Rutherford alpha scattering also we observe what is the closest distance of approach of alpha particle towards the nucleus. They won't come in touch, Nana. Then the question arises, because of this Coulomb repulsive force, if they won't come close to each other even, how can you say, sir, they fuse each other? Means one proton combines with another proton, means this proton enters into the nucleus of other. And altogether the nucleus becomes proton plus proton. 2 protons will be there inside. Okay. How to fuse them, sir? For that he is saying, now I think you understood why they selected the neutron as the target, sorry, as the bombarding element in the case of fission. Neutron is a chargeless particle, Nana. That's why very easily be captured by the nucleus. Why? Because there is no force of repulsion. That's why there we did not discuss this type of argument. Neutron is captured by the nucleus very easily, even though the energy is thermal energy 0.026 electron volts. Okay, but here in this case, we are directly trying to fuse the nuclei. Each nucleus has their own charge. Okay, that's why it is the problem, Nana. So here, because of that Coulomb repulsive force, we can't fuse each other. Okay, fuse these nuclei. Sorry, fuse these nuclei. Okay. If that is not possible, how will you discuss the nuclear fusion concept here, sir? Okay, for that, what he is saying, the major difference between fission and fusion, what he is saying, there to initiate the reaction, okay, some neutron is required. Neutron is required. Neutron initiates the reaction. Better I write here the differences simultaneously so that you can understand what is going on there and here in nuclear fusion and fission. Okay, without any confusion. So here, suppose first I write fusion on the other side and fission this side. Okay. First point, how to start the reaction. In fission, it is very simple. To initiate the reactions, here I say neutron is required. And that neutron easily be captured by the nucleus because of neutral particle. Okay. Whereas fusion, now only we discussed the villain in this part in fusion also is the Coulomb repulsive force. So forcibly we want to bring them close to each other. Forcibly means we have to give lot of energy for the two nuclei. How will you give, sir? For that to initiate what he is saying, the reaction, first of all, a high temperature is to be maintained. Means we are supplying the energy in the form of thermal energy. Okay, heat energy. By that means how much temperature is required, sir? Almost equal to the temperature on the surfaces of stars. Means nearly 10 power 7 or 10 power 8 Kelvin. Yeah. That's what I'm saying. Okay, high temperature. Okay, nearly 10 power 7 or 8 Kelvin. Okay, temperature what we have to maintain. Sir, at that high temperature, first of all, the humans can't sustain, sir. That's why here it is highly impossible to construct the fusion reactors. Why? Because at that high temperature, usually no matter exists. Okay. Even though if you take the fuel, that will be converted into here the nuclei separately. All the electrons will be stripped off from the elements, and bare electrons and bare nuclei will be seen there in that matter. Such type of state is usually we call that as a plasma state now. That's why in all books we see on the surface of sun we can see the plasma state. Plasma state means the nuclei are separated from the electrons because of this high temperature. Okay, directly the nuclei will try to combine. This is the main disadvantage. But simultaneously, on the other hand, if you see here, to initiate the reaction, neutron is required, but the fuel, whatever you are taking here, is radioactive. This is the advantage. Easily you can initiate the fission reaction. But the disadvantage on the other side is you have to take the radioactive element. Okay, radioactive is very dangerous, we know. It emits continuously alpha, beta, gamma rays. They are very harmful to the humans. Okay, this is the disadvantage on the side of fission. Whereas on the side of fusion, if you see there, the fuel is not radioactive, is non-radioactive. Okay, but the disadvantage is to initiate the reaction, high temperature to be maintained. Usually on the surface of Earth, it is very risky to maintain this high temperature. Why? Because we can't sustain at that high temperature. And number three, here, the fragments also radioactive. This is one more disadvantage on the side of fission, if you see. Fragments are radioactive. But if you see on the other hand, fusion, you see here helium. This is stable and inert gas, that too. This is non-radioactive. That's why here on the other side, you can see the advantage after initiating and completing the fusion reaction. The fragments, data nuclei, if you see, all are non-radioactive. Directly, you can leave at any place, those fragments. Okay, no need to take care. So here the fragments or daughter nuclei are non-radioactive. Okay, the advantage here for demolition purpose or else for constructive purpose, destructive or constructive purpose, you can create the nuclear fission reactor. Okay, or you can use it in wars for demolition purpose. Okay, so here we can write the energy released can be utilized for constructive or destructive purposes or destructive purposes. Okay, what is this spelling? Okay, and here spelling correct?
Yes.
Okay, right. Whereas here, yes, correct one. Thank you. Whereas here fusion problem is the energy released, okay, can be utilized, but not possible on the surface of Earth. That's why here till now, even though this much science is developed till now, until now, what I say, we did not see any kind of fusion reactors on the surface of Earth. This is the disadvantage. Even though we know there are no radioactive fragments, the fuel is not required, is not radioactive. Okay, we are unable to start the fusion on the surface of Earth because of the very first point here, what we discussed. Initiation is not so easy on the surface of Earth. Okay, but later if you see, compared to that, even though in each reaction, means here if I write the next point in the fission and fusion, here what I write, even though the energy released in a reaction is more, the amount of energy released for given amount of mass is comparatively less. Comparatively less. Okay. Here this is what I say, same fifth point other side. The energy released in a reaction is appeared to be less. Appeared to be less. But for the given amount, for the given amount of, but here I write, but for the given amount of mass, the energy released is more. Okay. So here, if you observe sixth point, it can be controlled. If you want to control by using like moderators and control rods, you can control. That's what we are doing in the fission reactors. Okay. By using control rods. But here what I say, once the reaction is initiated, it is not so easy to control. Okay. So it becomes uncontrolled once the reactions are initiated. Means what I am saying, controlling of fusion is not so easy. Why? Because here directly the nuclei are trying to combine. If nuclei are there, continuously they try to combine at that temperature. That's why it becomes uncontrolled. These are the disadvantages what I am seeing here in fusion compared to the fission. Okay. When I come back to here, directly, sir, you can't fuse these two unless you maintain at that temperature. But problem, even though at that temperature also, directly they are not combining. That's why here, of course, no one saw and went to the surface of sun and no one observed. Some predictable reactions they proposed. Okay. So here to fuse, to get final these reactions with the help of catalyst in the middle, the proposed reactions are proposed cycles, what we say. For nuclear fusion or first one they said, this is carbon nitrogen cycle. Simply we say CN cycle, carbon nitrogen cycle. What is this carbon nitrogen cycle, sir? What is that cyclic process? Yes, observe here. Directly, the four protons are not combining here. How they combine, sir? Using the taking the help of catalysts. Who are the catalysts, sir? Observe here in the reaction in a cyclic process. First, on the surface of some star or on the surface of Earth where the gases are present. Okay, there C612 combines with one proton at the high temperature. This is pakka required initially to initiate the reaction. One proton is captured by C612. Okay, releases C613 plus some amount of energy. Okay. And immediately the C613 disintegrates into here. Uh, 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 no, I think. Next, again, it combines with one more proton, and it is converted into N714 plus some amount of energy. Okay. Yes. Next, N, is it correct, Anna? I think it is wrong.
C13 7.
Ah, this is wrong, na.
Yes, sir. That's what C30. 7 other
Not C,
element.
Nana.
Some other element.
6 plus 1, another element. C, 6 plus 1, 7. 7 and nitrogen.
Yes, sir.
Yes. Yeah, it becomes, transforms into N713 and energy. Yeah, correct. This one, N713, exactly, now it is correct, is disintegrated into C613 plus 1. One positron will be released, of course, plus some amount of energy. Okay. Yes, that C613 combines with one proton, two protons. Okay, right. And releases C6 plus 1, 7. N714 plus some amount of energy. And this is stable. Okay, right. N714 plus one more proton combine, and this releases O815 plus some amount of energy. It is unstable. Okay. So O815 disintegrates into N715 plus one positron. Of course, because of mass defect, some amount of energy. This is also unstable. So N715 plus combines with H11 gives rise C612 plus He24 16 8. Okay, right. Plus some amount of energy. Again, what I have to write, C612 plus H11. You observe that one only, the first reaction here I took. Means after this reaction, the same cycle once again starts. Again, that released C612 combines with one proton, same blah, 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 1, 2, 3, 4, 5, 6, 6 reactions. Again, C612 will be formed. Again, that combines with the proton. Means the same cycle repeated like this. That's why it is called as one cyclic process. Now you understood this point, Nana? This cyclic process starts
Yes.
with the C612, ends with C612. Again, that C612 combines with H11. The cyclic process again starts. So here you observe this one, you take it as one reaction, combination of 1, 2, 3, 4, 5, 6 reactions. Okay, all together if you add, okay, then here you can identify who are the catalysts in the reaction and who are finally appearing in the reaction as one reaction, one in a cycle. Here finally C612, this is C612 get cancelled on other side. N713 will be cancelled here. C613, N714 and AO815 also get cancelled. N715 also get cancelled. So on the left hand side, you are seeing 1, 2, 3, 4 protons altogether. After adding the 6 reactions, you found that. And on the right hand side, after cancelling these reactions here, finally you are getting what the energy plus 1, 2 positrons there, and He24 is not get cancelled on the other hand, Anna. So He24 plus altogether the amount of energy is some Q. That Q is how much already I told here, nearly 23 to 27 MeV. Okay, this is one cyclic process proposed by the scientists. Okay, here they assumed this is as one reaction. By this, four protons combine to form He24 and releases the energy, where the gases are present, not escaped from the surface of stars. Okay, where the gases are present, sir, in every burning star. Okay, right? Not power star, superstar. No. Burning star means who are the livelihood, who are now emitting some energy from their surface. Those stars, including the sun. Okay, and all the stars means simply glowing stars. What I say, right? On the glowing surfaces of stars, you can find all the gases, and these reactions are possible. What they proposed. Okay. Sir, if you see not a burning star, sir, like some dim stars, sir. Who are the dim stars? Usually suppose this fuel, which is required for the fusion, the fuel is a proton. Those protons availability is almost exhausted on the surface of star. Then what happens? The reactions for protons are not available there. Then immediately reactions stop suddenly. When the reactions start, released energy will be not there. If there is no energy, then immediately the star tries to cool by itself. When the star tries to cool itself, all the solid matter here tries to come shrink. That's what we say. Come close to each other, and compared to the gas, that mass, solid mass, tries to separate. At that time, what happens? The gravitational pull on the gas particle will be decreased compared to the solid particles, and the gas particles try to slowly go away from this surface of star. Means that expansion of gases you can see here. That too, temperature is there on the surface of star. Okay, already it is hot, and now it is cooling, and that is releasing the energy, and the gas molecules easily absorb that energy and try to escape from the star. That time we can see the separation of matter from the gas. Matter means solid mass from the gases. At that time, you can see the star will be appear like a giant pan, very big one, giant one. That giant one is called as giant star. Okay, when you are seeing the expansion of a star, okay, giant star means whose size is almost becomes 10 times to the present size. Okay, that giant star, and finally those gas molecules velocity here will be that too, they are going away from the mass. At that time the gravitational pull will be less, and at that height the escape velocity will be less. That escape velocity, suppose, is greater than the RMS velocity of the gas molecules, what we learned in the kinetic theory of gases. Okay, the RMS speed is greater than the escape velocity, then immediately all the gas molecules escape from the star. When the gas molecules, all the gases escape, previously because of gas molecules, the star is appeared like a giant star. Suddenly appears when the gas molecules escape from the surface, that you can see like one big explosion. Okay, what we see, that big explosion, and then here all the gas molecules escape. Suddenly the star appear like a dwarf. Okay, why? Because the giant part means the gas molecules, all these gas molecules escape, so the only solid matter will be appeared on the star. That star is called as dwarf star. That is dwarf star, we call it as a dim star. Okay, again, since because of gravitational pull, all the solid molecules try to come to close to each other, but still they are also like ions. All the protons are already stripped off from the solid matter. Okay, and those protons here again try to combine. Okay, again try to release some less amount of energy compared to the burning star. Okay, that reactions, possible reactions, here they proposed another cycle. That cycle is called as proton-proton cycle. Okay, you can't take the help of oxygen, nitrogen, all these already escaped Nana from the giant star because of explosion. Proton-proton cycle. That's why they can't take the help of nitrogen, oxygen, carbon, and all. Only protons will be there on dwarf star. Okay, that cycle assumption, scientists' assumption, they proposed one cycle here. Again, why the dwarf star, dim star is releasing still some amount of energy here. They explain like this. Are you able to follow, Nana, my explanation?
Following, sir.
Yes, sir. Yes, sir.
Yeah. Carbon nitrogen cycle and proton proton cycle. Okay. Here you won't see these kind of thank you. These kind of here reactions. We have to propose only with the protons, not with the help of oxygen, nitrogen, carbon. Okay. There they propose like this, like H11 straight away. Okay, here the gravitational pull tries to dominate here. Why? Because that also the inversely proportional to R square. Electrostatic repulsion also inversely proportional to R square. You are getting some help from the gravitational pull. Okay, and here because of that gravitational pull, there is a chance here the protons again combine. When they come because of gravitational force of attraction. It releases H11 plus H11 gives rise H12 deuteron, nucleus deuteron, correct only, plus one positron. The reaction balance nana 2, correct, plus some amount of energy. Same they proposed one more reaction, means same 2 times they assumed, means H11 again combines with H11 or releases same H12 plus A plus 1 0 plus some amount of energy. Instead of writing these the same reaction 2 times, you can write into 2 also. That is also correct. Okay. And again, this H12 deuteron combines with one proton, and that 1 plus 1 2 He23 plus some amount 2 2 1 plus correct. So balance, reaction is balanced, some amount of energy. Again, you can write into 2, means same reaction one more time I'm assuming. Plus one proton gives rise here He23 plus some amount of energy. Okay. Now this one 2 times and the second reaction also 2 times, both 2 times they proposed, scientists proposed, and released He23 and He23 directly they combine it. And here the one releases He24 plus 2 positron, no, 2 proton. Why? Because 4 plus 2, 6, 3 plus 3, 6, 2 plus 2, 4, correct. 2 proton plus some amount of energy. This was one cycle they proposed. Again, you observe here, 2 protons are released. Those 2 protons again initiate these 2 reactions. One proton with again one proton, another proton again with another proton, leaving He24 there. Means when you come to this part, again I have to propose these 2 reactions. Means cycle again starts. So the cycle ends here, again starts the same part from here. Now you understood this one, Nana? Or any confusion here?
No,
Good.
yes, sir.
All right, good.
Sir, one doubt, sir.
Here,
ఎస్ సార్ అంటే ఇప్పుడు ఈ ప్రోటాన్ సైకిల్ ఏమో డిమ్ స్టార్ లైట్ అన్నారు కదా సార్.
yeah.
సార్ మనకి అదే డిమ్ అవడానికి కారణమే ప్రోటాన్స్ సరిపోక రియాక్షన్ ఆగిపోయింది కాబట్టి అలా ఉంది కదా, అయింది కదా సార్. మరి ఇక్కడ మళ్ళీ ప్రోటాన్ తోనే రియాక్షన్
కాదు ప్రోటాన్స్ అక్కడ తగ్గిపోయి గ్యాసెస్ లో ఉండే ప్రోటాన్స్ తగ్గిపోయి నీకేమవుతుందంటే మ్యాటర్ అంతా కూడా ప్లాస్మా స్టేట్ లో ఉంటుంది కదా నాన్న.
ఎస్ సార్.
ఓకే, ఆ టైంలో హూస్ హెల్ప్ ఇట్ టేక్స్ అంటే నాట్ ద హెల్ప్ ఆఫ్ మ్యాటర్. ఓకే, అదంతా కూడాను విత్ ద హెల్ప్ ఆఫ్, ఎందుకంటే ఈ మ్యాటర్ అంతా కూడాను ఆక్యుపైడ్ బై, అంటే ఇప్పుడు ఎర్త్ ఈజ్ సరౌండెడ్ బై గ్యాస్ టైప్ లో, అంటే ద అట్మాస్ఫియర్. అంటే ఈ అట్మాస్ఫియర్, ఆల్ ద గ్యాస్ మాలిక్యూల్స్ కమ్ క్లోజ్ టు ద సర్ఫేస్ ఆఫ్ ఎర్త్ బికాస్ ఆఫ్ టెంపరేచర్. ఓకే, అవన్నీ వచ్చి అక్కడ రియాక్షన్స్, అందుకే దాన్ని కోర్ రియాక్షన్స్ అంటాం. ఓకే, కంపేర్ టు ద స్ట్రాటోస్ఫియర్, ఇవన్నీ ఐడియా ఉన్నాయా? సర్ఫేస్ అండ్
Yes, sir.
ఎడ్జెస్ ఆఫ్ ద సన్. యా, ఇక్కడ ఎట్ ద కోర్ ద రియాక్షన్స్ విల్ బి మోర్. ఇక్కడ ఏమవుతుందంటే దీస్ ప్రోటాన్స్ నెంబర్ ఇన్ ద గ్యాసెస్ విల్ బి లెస్, అంటే గ్యాస్ తో జరిగే రియాక్షన్స్ తగ్గిపోతాయి నీకు అక్కడ. సో దట్ వాట్ హ్యాపన్స్, వాట్ ఎవర్ ద సరౌండెడ్ గ్యాస్ మాలిక్యూల్స్ ఆర్ నాట్ ఇంట్రెస్టెడ్ టు పార్టిసిపేట్ ఇన్ ద రియాక్షన్స్, అక్కడ ప్రోటాన్స్ లేవు కాబట్టి. That's why suddenly with the gas molecules the reactions are stopped. That's why immediately those gas molecules tries to escape. కానీ మ్యాటర్లో ఉండేటటువంటి ప్రోటాన్స్ కంబైన్ అవ్వాలి అంటే మళ్ళీ అవన్నీ దగ్గరికి రావాలి. అంటే ఈ స్టార్ యొక్క మ్యాటర్ అంతా కూడాను బికాస్ ఆఫ్ హై టెంపరేచర్ ఆల్రెడీ ఎక్స్పాండెడ్ స్టేట్ లో ఉంటుంది కాబట్టి దట్ షుడ్ కమ్ క్లోజ్ టు ఈచ్ అదర్, మళ్ళీ దగ్గరికి రావాలి. అంటే కాంట్రాక్షన్ స్టార్ట్ అవ్వాలి, అంటే టెంపరేచర్ షుడ్ బి డిక్రీజ్. టెంపరేచర్ డిక్రీజ్ అవ్వాలి అంటే వన్స్ దీస్ రియాక్షన్స్ ఆర్ స్టాప్డ్ దెన్ ఓన్లీ ద టెంపరేచర్ ద కోర్ విల్ బి డిక్రీజ్. అర్థమవుతుందా?
ఎస్ సార్.
అప్పుడు ఈ మ్యాటర్ ఎక్స్పాండ్ అయినటువంటి మ్యాటర్ అంతా దగ్గరికి రావడానికి ట్రై చేస్తుంది. దట్ టైం ఏమవుతుంది, ప్లాస్మా స్టేట్ లో ఉన్న ప్రోటాన్స్ కూడా మళ్ళీ కంబైన్ అయ్యి న్యూక్లియై కింద కన్వర్ట్ అవడానికి ట్రై చేస్తుంటాయి. గ్యాస్ మాలిక్యూల్స్ ఏమో ఇక్కడ మళ్ళీ దగ్గరకు వస్తుంటే రిలీజ్ అయ్యేటటువంటి ఎనర్జీ, లాస్ ఆఫ్ ఎనర్జీ అవి తీసేసుకొని ఎస్కేప్ అవడానికి ట్రై చేస్తున్నాయి గ్యాస్ మాలిక్యూల్స్, రియాక్షన్స్ జరగట్లేదు కాబట్టి. సో ఇదంతా కూడా ఎక్స్పాండెడ్ స్టేట్ లో కనపడుతుంది మనకి. ఓకే, ఎప్పుడైతే ఇవి వెళుతూ 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 అన్ని దూరంగా వెళ్ళిపోతాయి, ఇక మనకు ఓన్లీ డ్వార్ఫ్ ఒక్కటే మిగులుతుంది. ఈ డార్క్ మీద ఆల్రెడీ రియాక్షన్ స్టార్ట్ అయిపోయాయి వెన్ దే ఆర్ కమింగ్ క్లోజ్ టు ఈచ్ అదర్. ఓకే, ఆ రియాక్షన్స్ హీ ఈజ్ సేమ్. ఇప్పుడు అర్థమైందా?
ఎస్ సార్.
అంటే ఇప్పుడు రియాక్షన్స్ ఆర్ గోయింగ్ ఆన్ విత్ ద మ్యాటర్ మాలిక్యూల్స్ ఆర్ గ్యాస్ మాలిక్యూల్స్, అంటే
మ్యాటర్
గ్యాస్
దగ్గర
ప్రోటాన్స్, యా మ్యాటర్ లో ఉండే ప్రోటాన్స్, నాట్ విత్ ద ప్రోటాన్స్ ఆఫ్ గ్యాస్. ఓకేనా?
ఓకే సార్.
ఇది కూడాను ఎక్కువ టైం ఉండదు మనకి, ఇది కూడా ఎక్కువ టైం ఉండదు. వై? బికాస్ అక్కడ ఉండే ప్రోటాన్స్ కూడా కంబైన్ అవును మొదలెట్టాయి అంటే కూల్ అవుతున్నాయంటే మళ్ళీ దోస్ ప్రోటాన్స్ వోంట్ కంబైన్. ఓకే, మ్యాటర్ అంతా దగ్గరికి వచ్చేస్తుంది, డ్వార్ఫ్ అయిపోయింది కదా నాన్న.
ఎస్
ఇలా
సార్.
దగ్గరకు వస్తూ ఉన్నప్పుడు ఇంకా చాలా, అది సరే ఇదంతా కన్వర్టెడ్ టు బ్లాక్ హోల్, ఇవన్నీ మనకి అవుట్ ఆఫ్ సిలబస్ కాబట్టి ఇప్పుడు అవసరం లేదు. జస్ట్ ఓకే, జస్ట్ స్మాల్ ఇంట్రడక్షన్ ఐ గేవ్ దేర్. ఇది నాన్నది. ఇంకేమైనా డౌట్ ఉందా ఇందులో?
నో సార్.
నీ డౌట్ క్లియర్ అయినట్టేనా?
క్లారిఫైడ్ సార్.
Okay, then good. Then coming to here, after adding all the reactions in one cycle, if you add, okay, then you are getting here. If you see two protons here, cancel with the two protons, and here 2 plus 3 plus 1, 4. Altogether 4 protons are there. And in the same way here, H12, H12 cancel, He23, He23 cancel. So altogether here I am finding out 2 positrons and 1 helium nucleus. He24 plus 2 positrons, H11 plus some amount of energy. Okay, this is the story what they proposed, Nana. And the same thing also you can start from here. He23 plus like here, Nana, H12, H12 there, na. So those same thing here, or they proposed one more, H12 plus 1 proton releases here He23 plus some amount of energy, and this one they propose 2 times, and H12 plus sorry, same already I wrote 2 times, and He23 plus He23 gives rise here, sorry, He24 plus 2 protons plus some amount of energy. Okay, Nana? So here, if you see this one also, okay, here not proton, Nana. Protons get cancelled. If you add He23 also get cancelled. Deuterons, 2 deuterons, if you add H12 plus H12, 2 deuterons, 2 times deuterons, gives rise He24 plus some amount of energy plus Q. Okay. This is another possibility with deuterons, what they told. Okay, the 2 possibilities they explain here. ఇందులో ఏమైనా కన్ఫ్యూషన్ ఉందా నాన్న? Any confusion is here for you?
Sir,
Is there any confusion? Yes, yes.
Sir, this proton cycle ఉంది కదా సార్, అది డెడ్ స్టార్ దగ్గర అవుతుంది కదా, డిమ్ స్టార్, అంటే దానికి నెసెసరీ హీట్ వస్తుందా?
ఎక్కడ గ్రావిటేషన్
proton cycle
they are coming very close to each other కదా. మరి కమింగ్ క్లోజ్ అంటే లాస్ ఆఫ్ ఎనర్జీ ఏమవుతున్నట్టు? Until the gas particles escape, they are taking the energy. Later, what happens?
They'll come close.
Yeah. Already they are coming close to each other. That too, the released loss of energy is converted into, is absorbed by these molecules or the protons or the deuterons, and they combine.
Okay.
Okay. Right. But చాలా స్టోరీ ఉంటుందిలే నాన్న, మనకి అది అవుట్ ఆఫ్ సిలబస్ కాబట్టి వీఆర్ నాట్ డిస్కసింగ్, జస్ట్ బ్రీఫ్లీ వీఆర్ డిస్కసింగ్. ఓకే, ఇది దీని యొక్క స్టోరీ నాన్న. సో ఎనీ డౌట్ హియర్ ఇన్ ద వన్ డ్యూట్రాన్ సైకిల్ అండ్ ప్రోటాన్ సైకిల్? ఈ రెండిట్లో ఏమైనా డౌట్ ఉందా నాన్న?
నో సార్. నో సార్.
అంటే ఇక్కడ నుండి స్టార్ట్ చేసి
ప్రోటాన్ సైకిల్లో సార్ లాస్ట్ కి అది 2 పాజిట్రాన్స్ కదా సార్, లాస్ట్ నెట్ రియాక్షన్ లో 2 పాజిట్రాన్స్ కదా సార్?
రియాక్షన్ రాయడం తప్పు రాసాను కదా. యా, యు ఆర్ రైట్, 2 పాజిట్రాన్స్, E+1 ఇది కరెక్ట్ గానే ఉందా? H11 క్యాన్సిల్ అయిపోయింది, He23 ఇది కరెక్ట్ గానే ప్లస్. ఓకేనా? These 2 reactions only I wrote here initially. H12 plus H12 gives rise He24 plus some amount of energy. What I wrote, 2 deuterons, and 4H11 gives rise He24 plus 2 positron plus some amount of energy in both carbon nitrogen cycle or proton cycle. Okay, so finally we are writing what they propose, scientists propose. It's not my proposal. What they propose, carbon nitrogen cycle is possible, what they said, on the surface of burning stars, means hot stars. Okay, and these are burning stars. And proton cycle is possible on the surfaces of dim stars. that what we say white dwarf. Okay. These are the two possible reactions, possible only on the surface of stars, Nana, not on the surface of sun, Earth or planets or satellites. Okay, why? Because the initiation which is required to initiate the reactions is not possible on the surface of planets. High temperature is required. That will be here not possible on the surface of planets. Okay. At the time of evolution of this universe, according to our Big Bang theory, what they told, the total matter exploded, and then we find a few hot masses and cold masses. Hot masses, they named them as stars, Nana. Okay, that what they proposed on the surface of stars during the evolution of that universe only we can find these reactions, the initiation of reactions, not in the middle. Okay, that's all. This is nuclear fusion, and we can conclude that here in, suppose if I take a note what I'm writing, this last point what I'm going to write today. Here what I say, suppose if I take 1 gram of the proton, okay, how much amount of energy will be released? Releases how much amount of energy? That if you see here, according to Avogadro's principle, here H11 means 1 gram of uranium, sorry, proton contains Avogadro number of nuclei, Nana. Okay. So here, these number of nuclei, 1 gram contains these number of nuclei means, out of those nuclei, if 4 nuclei combine, and gives an amount of energy of nearly some 27 MeV. Okay. Suppose 6 into 10 to the power of 23 nuclei combine, how much amount of energy will be released? That we can write it as the energy released in fusion is equals to, I have to write 6 into 10 to the power of 23, that is Na into 27 MeV divided by 4. Okay, in fusion of 1 gram of proton. Okay, this is the amount of energy released. Means that is equals to, if you see here, that equals to Na into 4 sevens are 28, approximately 7 nano. I am getting energy released 1 gram of fusion. Okay, fusion of proton means hydrogen. If you see here, Na into 7 MeV of energy release we found. Whereas 1 gram of uranium, fission of uranium 235, already you know that that is Na into how much, Nana? Remember, 200 by 235. I think all of you forgot this one. 1 gram of M into Na into E by A. Formula మర్చిపోయారా? Energy released in fission.
8.17 inch.
Yeah. This is approximately equal to 1 into Na. Okay, 200 by 235, 0.9 something you will get, Nana. Okay, so you observe here both 1 gram of uranium and 1 gram of hydrogen if you take, there you are getting more amount of energy. In each reaction, the energy will be less. For given amount of mass, the energy is more. How many times more you are seeing there, Nana, compared to the fission?
7 times.
This one what I wrote in the table. Even though the energy released in a reaction is more in the fission, the amount of energy released for given amount of mass is comparatively less in fission, comparatively more in fusion. So the last point I concluded here, that implies energy released in fusion, okay, per each gram, 1 gram is equals to 7 times to energy released in fusion per gram. Sorry, this is fission, no? Fusion is 7 times energy released in fission per gram. Is my conclusion correct, Nana? Any mistake is there?
No, sir.
Right. This is the conclusion. And here finally, we are saying that fusion is uncontrolled, fission you can control. So shall I stop it now, Nana? The class?
సార్ ఒకసారి ఆ కార్బన్ నైట్రోజన్ సైకిల్ పెట్టరా?
Okay, sure.
సార్ ఇందులో ఇక్కడ సార్ ఇప్పుడు 8 ఆక్సిజన్ 815 ఉంది కదా సార్, నెక్స్ట్ పేజ్. అది మారే
ఇక్కడ
అది మారే సార్ నైట్రోజన్ 715 ఎందుకు అవ్వాలి సార్? వేరే ఇంకేమన్నా అవ్వచ్చు కదా?
అవ్వచ్చు, వాళ్ళ ప్రపోజల్ అలా పెట్టారు. 815 అనేది అన్స్టేబుల్ గా ఉంటుంది కాబట్టి అది ఒక పాజిట్రాన్ ని రిలీజ్ చేసి, అంటే ఒక రేడియో యాక్టివ్ ఎలిమెంట్ లాగా బిహేవ్ చేసి, 815 రేడియో యాక్టివే, ఆర్టిఫిషియల్ రేడియో యాక్టివ్ ఎలిమెంట్ ఇది. అది ఒక పాజిట్రాన్ ని రిలీజ్ చేసి, అంటే 1 పాజిటివ్ బీటాని రిలీజ్ చేసి N715 గా కన్వర్ట్ అవుతుంది అనేది ఒక ప్రపోజల్.
అంటే ఇప్పుడు అది నేను ఎలా అనుకున్నా అంటే, ఒకవేళ 2 బీటా పాజిటివ్ రిలీజ్ చేసి 6C15 అవ్వచ్చు కదా?
అవ్వట్లేదు, ఎందుకంటే ఇది న్యాచురల్ గా కూడాను 815 ఆర్టిఫిషియల్ ట్రాన్స్మిటేషన్ తర్వాత అబ్జర్వ్ చేస్తే ఇట్ ఎమిట్స్ మోర్ పాజిటివ్ బీటా పార్టికల్స్ ఉంది.
ఓకే సార్.
అందుకని వాళ్ళు ఈ రియాక్షన్ ని ప్రపోజ్ చేశారు. ఓకే, ఆర్టిఫిషియల్ ట్రాన్స్మిటేషన్ తర్వాతనే కదా ఇవి న్యూక్లియర్ ఫిషన్, ఫ్యూషన్ ఇవన్నీ కూడా వాళ్ళు ఫైండ్ అవుట్ చేసింది. సో ఇక్కడ ఎర్త్ మీద ఏమేం పాసిబిలిటీస్ ఉన్నాయో, ఒకటి రియాక్ట్ అయితే అది అన్స్టేబుల్ గా ఉన్నప్పుడు దేనిగా కన్వర్ట్ అవడానికి ఛాన్సెస్ ఉన్నాయో చూసి ఆ రియాక్షన్స్ ప్రపోజ్ చేశారు. అండర్స్టూడ్?
Sir, once when you go to next second page.
Yes.
Sir, in fusion we wrote, no sir, the energy released in reaction is less. In fusion
is more in each reaction, and in a reaction is appear to be less in one reaction.
Okay, means for one single reaction it is very less, but for some particle
single reaction we never seen. We take like 1 gram, 1 ton, 1 kg, like comparison should be like for given amount of mass kada nana.
Okay, understood.
That's why later I wrote here for given amount of mass.
Okay.
Here in a reaction 200 MeV appear to be in single reaction it will be more, but for given amount it is comparatively 7 times more. Fusion is more.
Okay.
Right. So do you want pages, Nana, or else directly shall I stop it now?
పెట్టండి సార్ ఒకసారి.
Right. First page.